This is the second lecture for Text Unit 3. In this lecture, we will discuss applications of stoichiometry, which we learned about in the last lecture. In particular, we are interested in the percent mass of elements and compounds and empirical and molecular formulas. Let's begin by considering a common compound, dihydrogen dioxide, commonly known as hydrogen peroxide. It's probably in your medicine cabinet at home, of course. The formula is H2O2. You could ask, what is the percentage of oxygen by mass in this compound? The law of constant composition assures us that that percentage will be the same in every sample. Here is how you answer this type of question. First step is find the molar mass of the compound. Second is find the molar mass of the element. Now there are 2 moles of oxygen in every mole of the compound, so you will need the mass of 2 oxygens in this case. And then divide the mass of the element by the mass of the compound and multiply by 100% to convert it to a percentage. Okay. So, the molar mass of H2O2 is 34.0146 grams. You should verify that for yourself. This is the mass of a mole of H2O2. Okay. The mass of 2 oxygens, or 2 moles of oxygens, is 31.9988 grams. You should verify that calculation. Right. This is the mass of oxygen in a mole of H2O2. 2 oxygens. Mass of 2 moles of oxygen. The percent oxygen is 31.9988 grams divided by 34.0146 grams. Grams cancel. Multiply by 100% to convert to a percentage. And since each of these factors has 6 significant figures, we express the percentage to 6 significant figures. This percentage will be the same in any sample of H2O2. Right, now you might see a question such as how much oxygen is in 1 gram of H2O2? When you see a question like this and it asks how much, typically it means how much in grams. Now, if you're confronted with a question like this is how you find the answer. Find the percentage of oxygen in H2O2. Now, we just did that calculation. Multiply that percentage in decimal form by the mass of the sample. In other words, we can use mass percentages to answer a question like this. You can attempt it at this point before moving on in the presentation and seeing the solution. Right, so again, if the question is how much oxygen is 1 grams of H2O2, the percentage is 94.0737%. We just calculated that previously. In decimal form, this is 0.940737. 0.940737 times 1 gram is 0.941 grams. Now on to a discussion of formulas. The molecular formula for a compound is the formula that shows how many atoms of each element are in a molecule, or in a formula unit in the case of ionic compounds. In other words, molecular formulas are the formulas you learned about in Text Unit 2. An empirical formula shows only the smallest whole number ratio of atoms of elements. Okay, so how is that different from a molecular formula? Okay, Consider the molecule of the day, dihydrogen dioxide. The molecular formula is H2O2. 2 H's to 2 O's. However, the ratio of H to O is clearly 1 to 1 from this formula. The empirical formula is just HO. Empirical formula tells you the ratio of hydrogen to oxygen. Clearly, a molecular formula provides you more information. It tells you each molecule has 2 hydrogens and 2 oxygens. Empirical formulas can be found using stoichiometry. To see how, let's consider an example. A compound contains 38.23 grams of C and 8.02 grams of hydrogen. What is the empirical formula? A problem like this is always solved using the same steps. And the first step is to find the mole ratio of elements and hence get the atom ratios. And the first step in finding mole ratios is to find the number of moles of each element. So we take grams of carbon, convert it to moles using a unit conversion factor of 1 mole over 12.011 grams. There are 3.183 moles of carbon. 8.02 grams of hydrogen can likewise be converted to moles with a unit conversion factor. There are 7.96 moles of hydrogen. Now, divide both of these numbers by the least number of moles. So, 3.183 mole is divided by 3.183 mole to give 1 for carbon. 7.96 is divided by 3.183 to give 2.5 for hydrogen. And the ratio of carbon to hydrogen is 1 to 2.5. We can write that empirical formula like this. Alright, ratios of atoms, however, have to be whole numbers. We have carbon 1 and we have hydrogen 2.5, essentially. No fractional atoms can exist in a compound, so multiply all the subscripts by 2 to remove the fraction. Okay, the answer for our empirical formula is C2H5. Alright, so here C is 1 to 4 significant figures. Typically you will see an integer or a simple fraction for other elements in the empirical formula. For example, we got 2.5 for the hydrogen. And we multiply by 2 to keep this ratio, but to remove the fraction. If you have an empirical formula, it's possible to obtain a molecular formula if you have the true molar mass of the compound. Suppose we're told the true molar mass of the compound we're looking at is 58.12 grams per mole. The molar mass of C2H5 should be 2 carbons, 5 hydrogens, 29.062 grams per mole. If we take the real mass and divide the mass from the formula, we get a number 1.99, close to 2. This means that the molecular formula can be obtained by multiplying the subscripts in the empirical formula by 2. In other words, the compound's formula is actually C4H10. A molecular formula must always be some integer multiple of the empirical formula. Another way of saying that is when you take the real mass, which you obtain from some experimental data, and divide by mass from the formula, you will always get a whole number. 1, 2, 3, etc. Right. This concludes the presentation for Unit 3, the second presentation for Unit 3.